to advanced strength of materials, I'll be covering order Bernoulli beam theory. And what that is a dimensional theory that is used to simulate structures. And these structures are slender in the cross-sectional direction compared to the length of that beam, of that structure. Those are beams. Beams are long and are longer than the cross-section in general. And that's a very good approach to simulate a lot of problems. So, for example, if you look at this classroom, you will see there are chairs here that are supported by something that look like beams. They're long, tubular. You can see it there. But using three-dimensional finite element modeling to simulate a tube that's long and has a uniform cross-section is not very efficient. You can then use beams instead to represent the behavior of say, a chair supports, rather using simplified methods. This very building you're sitting on, right now you're inside this building. This building is very likely being analyzed using beams because you have most of the structure here in civil engineering structures. A lot of the supports are made of beams. Some of them are taking the weight of the building. Some of them are support buildings, support structures. Some others are beams going across on the roof to provide, additional stiffness. Other applications consist of rocket engineering. So my area of expertise, it is possible to size a launch vehicle because the launch vehicle is very long. So think of a rocket, it's very long and slender. So it is possible to actually use beam theory to kind of size some of the aspects of the design by looking at the angle of attack during flight, the Mach number, the drag coefficient, the lift coefficient, the thrust, and the engine loading conditions, and the pressure inside the tanks. All that can be considered in a very simplified model using beams. And I may have the chance to go through one example so you can see how that looks, but it's possible that I may not have the bandwidth to cover that. And so moving forward here, what you see here is application of beam structures in various designs. On the right-hand side, you see beams being used as part of the arch structure, but also truss structures on the left-hand side. So the idea of beam theory started being developed in the 1750s, and the primary assumption that was made is that under deformation, when you deform the structure that's very long and slender, typically a thickness over length ratio of 1/15, what you're looking at there was that the cross-section will remain perpendicular during deformation. So let's think about that a little bit more in the context of I don't know if you've ever encountered, in my time we have McMaster for design. So you have this very thick handbook where you can actually buy materials from a catalog. Now everything's online. But say you could have a telephone book, which I have never seen now, like in thousands of years, but you have those, right? So if you were to bend those very thick structures, very thick books, you'll see that the edges will start slanting as you bend it. It will slant like this. And it will slant where you can see that every page is sliding against the next page a lot, right? But if you were to take a notebook, and if I can have a notebook that's thin from anybody, if you don't mind, I want to do a simple demonstration for you that if I were to do that with a notebook, I apologize for taking this. But if I were to bend it just slightly here, you can see that that cross-section is not changing much. It looks about the same. You don't see any, it's not shearing. The page is not shearing relative to, it's not doing this, right? It's not doing this. Pages are not sliding relative to one another. So that's what I mean. The cross-section of that beam stayed perpendicular to the neutral axis. So after the beam is getting deformed, you don't see that cross-section changing very much. You don't see that cross-section changing very much. So that's what you see there. On the bottom right, what you see is a shear load in a section and the bending moment acting on that section of material. So I'll move here to the next slide. If I were to take a little piece, a dx piece, so I took a dx piece out of here. So say I take a little section here, dx, so a dx there, and I looked at that section. So I look at that, and noting that this beam is subjected to a distributed load W. Here I'm using Q. Same thing. I'm just trying to show you what that looks like. On the left side, you have the shear load and the bending moment. On the right side, what you see here is that you have a little bit higher shear load and higher shear moment by an incremental amount, dm. And I can now apply equilibrium equations. So what do I have? I have summation of forces in the y direction equals 0. So I have this v here that's going upwards. I have v plus v dv, which is going downwards in a negative sense. And then I have q dx. So q times this length dx, q times dx gives me a total force going upwards. That's this term. You can see that v and v cancels out. So I get the dv dx equals q. So the derivative of the shear load with respect to x equals the pressure load applied on the surface. Okay. Any questions on that? I think it's very straightforward. If I now do equilibrium of moments, you can also see here that if I do it about, say, I can do it about the center if you want to. I can do it about this point. In this case, I did about this point. So I did moments about that. So I have, if I take this as positive, then I have M there. That's that one here. That means different colors, you can see it better. That's that M there. And then I have M plus dm there, which is going the negative sense. You can see it there. And then I have V. That's this one here. V times this dx should be the amount of moment. And it is in the positive sense according to this convention. And the reason is because you can put your hands and your fingers so that they're aligned along the load, and then you're then rotating in the direction of the distance we're looking at here. Okay. Then you have the load applied due to pressure, which is Q dx. And then the dx over 2 is the fact that the total load here is applied in the middle. And so this distance here is dx divided by 2. So now you can see here that M cancels out. And then you can take, divide the whole thing by dx. And when you divide everything by dx, what you find is that dm dx equals V as dx goes to 0. So I invite you to try that at home. I think you will find that it's going to work out for you, that's what you're going to get. Secondly, what you see here is that if I plug in the definition of V into this equation here, into the very top there, and let me draw this again so it's clearer. So I put this into this V there. What I get now is the second derivative of the moment with respect to X is Q. Q being the pressure load applied. So again, moment is an internal quantity is actually an internal type force. It's similar to a force. That is your equivalent to stress, but now in beams. So beams stresses are internal force like quantities that react external loads, while moments in the shear here that you see are forces that react external loads for beam. Loads for beam, not loads. I apologize. So again, when I look at this beam, we're assuming that the cross-section stays perpendicular. You can see there that we drew the cross-section perpendicular to the neutral axis, so that let me ask that question. So if the neutral axis, the cross-section stays perpendicular to the neutral axis during deformation, what do you think is the shear strain gamma xy? If the initial angle is 90 degrees and during deformation, the angle is still 90 degrees, what is the shear strain? 0. Do you have a different answer? 0? Who else is saying 0? So is this shear strain 0? Is that what we're saying? How many vote that if the angle change is 0, the shear strain gamma xy is 0. What is the definition of shear strain? What is the definition of shear strain? If we look at the physical definition that was provided in class, shear strain is the angle change. And in this case, the angle that we're talking about is the one between the cross-section and neutral axis. If that angle is 90 degrees, and it's still 90 degrees after deformation, what is the angle change? What is the shear strain? 0. So this shear strain is 0. And so what we're saying then is that the deformations of the material only depend on the stretching of the outer fiber and inner fiber. Can everybody imagine me taking a beam and bending it? Do you agree that if I bend it as if you're smiling, the top surface will be in compression, the bottom surface will be in tension? The contributions for the deformation of that beam are only solely due to the fact that the beam is stretching the outer fibers and the inner fibers, but none of the shear strain is contributing to it, which is not the case for very thick beams. For very thick beams, like the notebook she provided to me, if that notebook was very thick and I tried to bend it, what you will see is there will be an angle change. That cross section is going to change quite a bit. That theory to attack that problem is called Timoshenko beam. It's out of scope for this course, but it's covered in my other classes in like finite elements and energy methods. So if you're interested, you can look at my videos for that. But another assumption that is made in this theory is that the deflection here that you see here, that deflection is going to vary linearly through the thickness. So you can see there that that is the case. The deflection, it is linear through the thickness. You can see y is a coordinate. So that's that y. And we're also assuming is proportional to the slope of the beam. And that makes perfect sense because you can see here, and let's examine that together so you can see what's going on. So you can see that at the very top surface, if the thickness of this beam is h, and the neutral axis went right through the center, that the top surface is going to move to the left an amount minus h half derivative of w respect to x, where w is the deflection of the beam, while the bottom surface, the bottom point here, is going to move to the right as the beam is bending. And it's going to move an amount h half dw dx. So that is really the actual deflection, and that is an assumption that you make. You can make the theory more accurate by saying it's y squared plus some other constant, y cubed plus another constant. There are theories that go up to third order even. But Euler-Bernoulli assumed that the deflection of that beam can be accurately predicted by assuming there's a linear function of the coordinate in the y direction, and also it is proportional to the slope. And so I don't know if you've seen, have you ever seen this formula, sigma stress equals my over I? Have you ever seen this formula? There's a reason why stress varies with y linearly, and that comes from this fact, from that assumption. So this is just an assumption. This is an approximation. In real life, it looks like that for very thin beams, but that's coming from here. It's coming from here, and I'll show it to you that it comes from there later on. If I calculate strain now based on this assumption, which I think everybody agrees that that makes sense now, that this beam deforms in a way that it follows that slope, as you can see here, and that the deflection varies linearly through a thickness in that way, where the top, if I have a point here P, and I have a point here Q, that's this point P, and that's this point Q, that the top surface will move to the left, the bottom surface will move to the right, in the way I'm showing it to you here. Now, when you look at the strain due to that actual deflection assumed, if you remember, epsilon xx is a partial of u respect to x. Do you remember that formula? So you can see quickly that the derivative of that respect to x gives you this. That's your strain now. And now your strain, what this is telling me now is that the strain is proportional to the curvature, because second derivative means curvature, while the actual deflection depends linearly on the slope. Is that making sense to you? Does that make sense? So in other words, if I have a beam that looks like this after I deform it, is that a lot of curvature? If I have a beam that starts straight and then it looks like the one here, very smiley, is that a lot of curvature? Yeah, so then you have a lot of strain. That's what that's telling me, right? The more curvature, the more strain. But what is a strain at the neutral axis? 0. 20 points for you. Why is it 0? Because the strain is 0 at y equals 0 at the neutral axis. Yes, that's why it's switching between compression and tension. In what situation that strain may not be 0 then? It could be if I'm applying a load that way, P. In that way, then now you have a strain there now that's contributing to a strain in the neutral axis. Is that clear? So let me go now and look at the moment definition and this maybe even the sign convention here. You can see here that I'm pointing the y direction upwards. That's why I don't like us memorizing sign conventions, because honestly, it depends on how you define y. In this case, I'm defining y going up, but civil engineers will use y going down. But who writes most of your books on statics and mechanics materials? Civil engineers. So if you're an aerospace engineer, you can say y going up because that's where space is. So you can see a discrepancy there. And my preference is nobody memorizes anything. Just learn what the sign convention is relative to your coordinate system. So let's study that together. If I have a stress sigma xx, if you recall, sigma xx means the first index means the phase where that stress is acting, which is the x phase. You agree? And the second index tells you in which direction sigma xx is acting, and that's in the x direction. So that's correct, the way I plot sigma xx. And what I want to look at, I want to look at the contribution of sigma xx to the moments, the differential moments. And when I look at that, you will notice that I have sigma xx, but then I have that distance to take care of, that distance there from here to the top of it. That's your moment arm. That moment arm is y. And so sigma xx times dA is a force, d force, and then y times dF is the moment arm. And you see a negative sign, and I will not be worried about that, because if you look, you will see that the moment arm, if I were to draw it, it goes up like that. That's your y there. And if you put your hand along the y axis in that way, and then you rotate your hand so it points to the sigma xx, you will see that your thumb goes into the page. And if you notice, z goes out of the page. So it's in the negative sense. So moment in this case has a negative sign because of that. Do you understand why it's not a good idea to memorize? You just redo this procedure if you have a different problem so you don't get confused. Yeah, is this making sense to you? So now when I integrate this on both sides, I get the moment equals that formula. But guess what? Guess what? We all know that stress equals E times strain. So I'm sorry about that. I plug that in here. So I get the moment equals the integral minus integral y, the modulus, the strain epsilon xx dA. And then when I plug in the strain, wasn't the strain this one here? This one right there? Wasn't that the strain that I just derived earlier? So I put that strain in here, into the epsilon xx. And when I do that, I get that E w prime can be extracted outside the integral. You get the integral y squared dA, but integral y squared dA is the moment of inertia, I. It's a geometric property that's easy to calculate. So then, definitely, now we can say that moment equals EI times w prime x. And I'm not asking you to memorize this formula, but I'm showing you where the equations come from, so you're familiar with what the derivations are. So this is an interesting formula that should be known, is that the moment equals the modulus of the material times the inertia, the moment of inertia I, w prime, and that's what you got there. And so if this is a formula I had derived earlier, do you remember that formula I had derived earlier? I derived it here when I took the piece of dx, remember that? I'm going to use that because now I know moment. I know what moment is. Moment equals EI w prime. So I'll just plug that in there. And that gives me this formula here. And that formula tells me, gives me a differential equation for the deflection of the beam upon a distributed load Q applied. That's the formula. Any questions you have up to this point? And I am reading the chat comments. Thank you, chat. Appreciate that. Any questions you have so far on the materials provided so far?
Just to confirm, can you hear me?
Yes.
Okay, great. Just to confirm, W is the deflection in the Y direction, correct?
Yes.
Great, thank you.
Yeah, so that was provided here just to make sure. So you can see here in this diagram, that's what I meant. I apologize if that was not clear to you. And then you have boundary conditions. The boundary conditions typically, and I'll go through each of these, but you either have deflection known at that boundary, or the moment or the rotation is known, one of the two. You can have both of them known as well. And more importantly, what I'm showing in this chart is the different kind of boundary supports you can have. The simply supported beam is A, the overhang beam is B, then you have the cantilever beam on the right hand side is C. If you look at this boundary condition, what you have here is that the deflection is unknown. The deflection is known is 0, the vertical deflection, but the rotation is not known. That's something that you have to calculate. In this case, the same thing here. And in here, what you have is that the deflection is known is 0, but also the slope. The slope is not known. It is known is 0. So both deflection and slope are 0 in this case. But at this boundary, when I look at this boundary, I don't know the deflection and I don't know the slope. So those are things that you could find in this problem. Okay, so in the bottom, what you see are beams that are statically indeterminate. And what that means with statically indeterminate is that you have more unknowns than equations from Newton's law. And so that forces you to look at additional equations that come from compatibility. And I'll give some examples on that. There are very specific definitions here for each kind of beam that you may see. Simply supported, which means that it's pinned on the left side, but then it could be rolling on the right-hand side, but it's fixed in the vertical direction. Overhanging beam, where the beam can go past one of the boundary conditions, and then cantilever beam, where like a diving board, basically. So with that said, that concludes this particular lecture.